Hi everybody, my name is Dr. Christopher Collison and we're continuing with the class CHMP. It's quantum mechanics and we're into lecture 5 now. So what I'm going to do is start with a brief recap of the first 4 lectures, and then we're going to talk about what's coming up in this particular module. So we're in lecture 5 in here. And so to recap from lectures 1 to 4, what did lectures 1 say? Basically, quantum mechanics, very strange stuff. Matter may be particles, it might be waves, it might be neither, it might be both. We recognize that quantum mechanics is a required approach to understanding some of these new observations, the photoelectric effect, the black body radiation problem with the Rayleigh-Jeans theory, and also with the atomic line spectra. So we need quantum mechanics to address these observables. We also remember from lecture 3 how de Broglie introduces matter waves, which seem to align with Bohr's angular momentum quantization assumption, which all kind of stems from Planck's idea of packets of energy. So everything is kind of tying together in lecture 3 in here. So what are we going to do in lecture 5? So we've recognized the need to kind of understand waves, and quantum mechanics is often referred to as wave mechanics. So in this particular segment, we're going to understand and consider the classical wave equation. We're going to use a method of separation of variables to solve that wave equation. In this particular case, we're going to think about a string that's bound between two surfaces, kind of like on a guitar. And so we're going to think about those boundary conditions. So the amplitude is going to have to be 0 at the two ends of the string. We're going to recognize some oscillatory solutions which are going to show up a lot more in future weeks' work. And why are we doing this again? Well, we're doing this because quantum mechanics was developed by Erwin Schrödinger, and he recognized that a pattern effectively such that quantization could be described well with certain wave equations, and he saw these integers pop up in these wave equations, and that was kind of the connection that was necessary to move quantum mechanics forward. So let's jump into some of the math today, and I'll take you over to that right now. So welcome back. We've talked about the recap from lectures 1 to 4 and what we're going to cover in this class. So let's start by describing the particular case that we might care about, and we're going to think about a string that's attached to two walls, and we're going to think about how that string can be plucked, and that the amplitude of the string here is going to be equal to u, and that's a function, or in fact the position is a function of x and of time t. So if you will, u is this function, and we can have a value of u, by the way, at any position, because it is, after all, a function of x. So here's our x-axis. So at some point in time, the string will be perfectly in alignment with the center of its motion, and at another time, at some point later, we can imagine that that string is going to have a position such as this. So that position of the string at any point along that x-axis is indeed a function of the position and as a function of time. So there's a classical wave equation that describes this, and that wave equation is given as di squared u. Remember, u is a function of x and t, by di x squared, and that's equal to 1 over v squared di squared u by di t squared. So this is our classical wave equation, and v in general is speed at which the disturbance moves along the string. What's important is that we know that x and t are independent variables, and u is the dependent variable. So u itself, this u depends on x and y. So what we're going to think about first is, since this string, if we go back to the diagram, since this string is fixed at the two walls, we have some boundary conditions that are going to be important here. And the boundary conditions are that u, which is on the y-axis really, u at position 0 at time t, any time t, must be equal to 0, and u, it's really again on the y-axis displacement at any time t, but at position L, so here's position L, if I go back to my diagram, x is equal to L at that final wall, that second wall, that's also equal to 0. And this is really for all times. And these are, as I mentioned, the boundary conditions. And this is going to become very familiar to you as we start to look at something called the particle in the box idea. In general, a partial differential equation must be solved subject to certain boundary conditions. So that's the definition there of why we care about these boundary conditions. So what I'm going to talk about next is what shows up in section 2.2 of your textbook, chapter 2.2 of Macquarie, and this is the method of separation of variables. And we're also going to note at this point, that the Schrödinger equation, which came into play in chapter 4, I introduced it to you in the rules of the game, but the Schrödinger equation can be solved with this method. So what is that approach? What is this method of separation of variables? So the key step here is to assume, so this is the key step, so we assume that this function u of x and time here, we can assume this factors into a function, capital X in here, that's a function of little x position on the x-axis, multiplied by a time function, if you will, capital T, which is a function of time, little t. And how do we write that mathematically? So u of x and t is equal to, we're going to make this assumption, is equal to x of x and t of t. And again, we're going to use the vibrating string problem to help us as we move through here. So what we're going to do is we're going to plug this expression into the wave equation, and the wave equation we've got was up here. Okay, so we're going to replace the u of x and t in here with our new expression. And what does that become? So that becomes, now we still have our di squared, and that's x now of x, t of t, and that's by di x squared, and that again was equal to 1 over v squared di squared, again x of x, t of t by di t squared. So what we can now do, of course, let's put the brackets in place. What we can do is we recognize that this is a derivative, a second derivative in terms of x. So because t is not varying with respect to x, so we can rewrite this. We're going to rewrite this as shown. So we're going to bring the t outside, t of t, and that's equal. Now we're going to also bring the x out here, right? So we don't need that x in place here. So we've got now x over v squared, because now we're operating with this, we're taking the derivative, if you will, of t of t. Okay, so we have our new expression. The next step in this method is to divide. We're going to now divide by u, and we remember that's equal to x of x, t of t. So we're going to divide throughout by this value, and that means, of course, if we're dividing this expression here by xt, then the t on the numerator here is going to cancel, and what we'll end up being left with, of course, is simply x of x on the bottom in the denominator. And now we're going to write this no longer as a partial derivative, by the way, because we only have terms of x inside this derivative. Let's move this up. Is equal to 1 over v squared, and now we've got our t term in the denominator because, of course, the x will have cancelled. Okay, so we have a simplified expression, and we're going to recognize that this left hand side in here is only a function of x. Okay, so this is only a function of x, and this right hand side in here, fortunately, is only a function of time, of t. So we recognize that if there's only, the left hand side is only varying with respect to x, and the right hand side is only varying with respect to time, we can basically recognize that when we can change the left hand side independently of the right hand side, and we can allow for each of these expressions to be equal to some constant. What we're going to do is we're going to say the left hand side 1 over x of x d squared x by dx squared. I'm going to say that's equal to some constant k, and by the way, the right hand side 1 over v squared t of t d squared t of t by dt squared, that's also going to be equal to k. So we can vary this side, the left hand side here, until we've got a value of k, and we can vary the right hand side here until we also get the same value of k, and that k we're going to call our separation constant. So this k is going to be called our separation constant. The important thing here to recognize is when we've separated these terms. So if we want to, by the way, we're going to rewrite this equation. We're going to rewrite it as d squared x of x by dx squared. And remember, what we can do is we can bring this x up to the right hand side, but then we're going to subtract it. This is a format that we're going to get used to. We're going to call that kx, and that's going to be equal to 0. So this is called an ordinary differential equation as opposed to a partial differential equations. The coefficients, by the way, the coefficient of this term is a constant. It's 1, in fact. The coefficient of this x term in here is also a constant. So that means that this is a linear differential equation with these constant coefficients. What we're going to do is we're going to say, what we really need in here is to solve for this k term in here. What is this k? So let's have a look. So that k, is it positive, negative, or 0 even? Okay, we're going to ask ourselves that question. So let's actually first start with the case where we're saying what happens if k is equal to 0. Let's first assume, we'll look at this case where k is equal to 0. Okay, so now what we end up with in here, quite simply, is dx squared x by dx squared. That's equal to 0. And how would we get that? What would be the solution? A solution to that equation would be simply x of x will be equal to a1x plus b1. Okay, so of course if we take the second, well, taking the first derivative of this, we'd end up with a1, and taking the second derivative, taking the derivative of a1 in effect would give us the 0. So this indeed would be a solution. Now, of course, we still care about our string. This was the boundary conditions that we set. So let's remind ourselves of the boundary conditions, right? So u at 0, t is equal to x of 0 and t of t, and that would be equal to 0. So, and also u of L, that's when x is equal to L, that's the end of the string on the other side, and that's equal to x of L and t of t, that also needs to be 0. But the only way that this can work up here, for example, so if we plug in, for example, let's try plugging in x equals L. So the only way that this solution can work, we need x of x to be equal to 0 when x is equal to L, right, in order for this expression here to be 0. So in that particular case, okay, for the condition, for our boundary conditions to be met, we must have a1 equals b1 equals 0. In other words, that's the only way x can be equal to 0 when x, it's the only way that this expression for capital X can be equal to 0 when little x is equal to L. Okay, and we actually recognize that this is it's pretty useless because a1 is 0 and b1 is 0, our function is essentially 0. So we call this the trivial solution, and really what we need to do is just throw it away. But we're going to recognize that it exists, and then we're going to kind of throw it out. Okay, so that was the situation where k was equal to 0. What happens when k is equal to a positive number? So now let's assume, so part 2 here, we're going to assume that k is equal to 0. And we're going to actually use a convention here. We're going to use a form such that k is equal to k squared. And this allows us to think of any real number k. So it sort of gives us a few more options, but k is a real number. It could be a negative number, of course. That would still give us a positive value of k. So there's a larger set of solutions, if you will. And that d squared x by dx squared minus k squared x of x here is equal to 0. So we're now plugging in the k is equal to k squared in here. So our experience from this says that there's another solution in here that is an exponential. So we might say, let's try that solution where x of x is equal to some exponential term. We'll call it e to the alpha x. E to the alpha x. And we're going to say alpha is a constant, and that constant's to be determined, okay? So let's try plugging this into our equation. And of course, if we take the second derivative of this x expression, what we end up with is we're going to get alpha squared e to the alpha x. We're now going to recognize, well, we got the k squared in here, k squared multiplied by that function x in here, and that's equal to e to the alpha x. So now we have a new expression, and that's equal to 0. So we've just plugged in this solution into our differential equation, and here is our result. So again, we think about our boundary conditions, and when we think about our boundary conditions, remember we need that x of L is equal to 0. Okay, so let's look at our expression here for a second. In order for x of L to be 0, okay, if we put an L into our expression here, if we substitute for L here and here, okay, so now we're going to have two positive values, e to the alpha L and e to the alpha L on both sides. So the only way for this expression to be 0, okay, is basically for alpha squared minus k squared to be equal to 0. And that's a factor in here because we can factorize this expression, okay, and we would recognize that alpha squared minus k squared would have to be 0. So that would mean that alpha squared would be equal to k squared. And indeed, alpha would be equal to plus or minus k. So we can actually write this as a more general form because we have to recognize that alpha can be plus or minus k in here. So a solution x of x in here is equal to c1 e to the kx plus c2 e to the minus kx. And that ends up being our general solution. So this is a general solution. What's the problem with this? Well, actually, when you think about it, the problem with this is when alpha is equal to plus or minus k, that means that whatever the value of x in here, it can't be a solution to our differential equation. So let me elaborate a little bit. Here we have a general solution. We have a general solution to this differential equation. However, because we need these boundary conditions in place such that at x equals L we need to get a 0 value, it turns out that this ends up being a trivial solution. In that particular case, with the boundary condition, C1 equals C2, and that would have to be equal to 0. And the reason again that this is the case is because if we replace the x with an L in here, C1 e to the k L plus C2 e to the minus k L, the only way in this case that we can get a 0 value, okay, for x to the L, and that must be equal 0, the only way that we can get a 0 value is when C1 equals C2 equals 0, which is what I've written up here. So it turns out that the general solution in this particular case, once we have our boundary conditions, the general solution doesn't work very well. It doesn't work at all. So the next part to this lecture is to think about certain oscillatory solutions. And these are these wave solutions. And here in this situation, we're considering, in fact, we're going back to our idea of k being less than 0. Okay, so we're going to assume in here that this capital K being negative is going to give us something interesting that we can use when we have these boundary conditions. Actually, we can borrow from our early general expression or our earlier general solution. So we've got x of x is equal to e to the alpha x. And now because of this negative sign, right, if we come back up here, we recall that in our earlier expression, when we have our left-hand side in here. So here's our earlier expression. Okay, we've got a minus sign in here. So when x is negative, we're going to end up with a positive sign in that case. So let's write that down. So it's now going to be plus k x, the x equals 0. And we're going to plug in our exponential answer from before. So what that means is when we take the second derivative of the left hand side, again, we're going to end up with, of course, alpha squared e to the alpha x. But now we've got this plus sign in here. So it's plus our constant k times e to the alpha x, and that's equal to 0. And so now we recognize that alpha squared plus k equals 0 is a solution. And this means that alpha squared is equal to minus k. And of course, now what we might do is let's assume that k is equal to 1. Okay, then in that case, what we've got is alpha squared is equal to minus 1. And so alpha in that case would have to be plus or minus I. So we have a new possibility. So we're going to expand this a little bit. We're actually going to recognize that our solutions can be some linear combination of e to the ix and e to the minus ix, because they're both solutions in here. All right, and so we're going to write that down as follows. X of x is equal to c1 e to the ix plus c2 e to the minus ix. Now, I started this particular section by talking about an oscillatory solution. So how do we get an oscillatory solution out of this these exponential terms? Well, what we're going to do is use Euler's formula. And Euler's formula says the following: e to the plus minus I theta is equal to cosine theta plus or minus I sine theta. So we're going to apply Euler's theory, formula to this expression. And so what we end up with is C1, and inside we've got e to the plus ix. So that's like e to the plus I theta in here. So C1, and that becomes cosine x plus I sine x. And now we've got this plus C2 piece in here. So that's plus C2, and that's cosine x minus I sine x. And what we're going to do is factorize that. All right, we see the same factors in here: C1 plus C2 multiplied by cosine x plus, okay, we got I C1 minus I C2, and the common factor there is sine x. So C1 and C2, by the way, are just constants. What we're going to recognize, in fact, that because these are just constants in here, let's actually call this C3. And these are constants as well. IC1 minus IC2. Well, this is also a constant. Let's call this C4. So we now recognize the equivalence of these two expressions. Okay. On the one hand, we've got a solution that involves constants C1 and C2. So x is equal to C1 e to the ix plus C2 e to the minus ix. And then we have another expression down here where x of x is also equal to C3 cosine x plus C4 sine x. So we've compared these exponential terms, and we now actually have an oscillatory solution because we've got a cosine x function and a sine x function. And I hope that you see some similarity with problem 2.5 at the end of the chapter. So this was our general solution. Let me just come back to an assumption that we made early on. We basically made the assumption that k was equal to 1. In fact, we said up here k was equal to 1. Let's broaden this out a little bit. Let's actually rewrite this expression. So we had originally dx to the x, dx by dx squared. Instead of the k in here, we're going to retain our plus sign, right? Because we're going to say that that's a negative value, that k is negative, that the magnitude was 1 earlier. But we're actually going to call this beta squared x. And what we're going to say is, since when we said that we were allowing our function x of x be equal to e to the alpha x, this is still valid, but as we plug this in, we're going to end up, of course, with our alpha squared e to the alpha x plus beta squared e to the alpha x. This now means that we have alpha squared plus beta squared times x is equal to 0. Okay, that's what our original equation is saying in here. Another way of putting this is that this expression is equal to 0, and therefore alpha is not equal to plus or minus I, but it's actually equal to plus or minus I beta. And we go through the same derivation as I showed earlier, where we can actually rewrite this x term as an oscillatory function in terms of cosine and sine. So let's rewrite that now. You can go back and review, but x of x is equal to c3 cosine beta x plus c4 sine beta x. And what I want to do very briefly is talk about how, if this is a solution for our particular case where we have our boundary conditions, so we have our string between these two walls and x is equal to 0, x must be equal to 0, and at x is equal to L, we must have x is equal to 0, because this function, again, x multiplied by t is equal to u, and in both cases, the u, the 0 value in the y-axis, we know to be 0 at the point where the string is tethered to these two walls. So what can we say in here? Well, we can consider two particular cases, x of 0. So x of 0, when would that be 0? So the cosine of x is equal to 1. So if we plug a 0 in here, we're going to get c3. Okay, sine of x is equal to 0 is equal to 0, so that term is going to cancel. So we'll find that x of 0 is equal to c3. And that must be equal to 0, so this tells us that c3 is equal to 0. Okay, so we can basically say that because of our boundary condition with x equals 0 here, then c3 is equal to 0. That leaves us with our possible solution of x is equal to c4 sine beta x. So now, again, we use the boundary conditions to our advantage, because we also know that x of L must be equal to 0, which is equal to c4 sine beta x. And the only way that we can have x of L be equal to 0 is if this sine term in here, if beta x is equal to 0 or pi or 2 pi or 3 pi, because the sine of 0, pi, 2 pi or 3 pi is equal to 0. So beta x must be equal to 0. So beta x must be equal to 0, pi, 2 pi or 3 pi. How do we write that? Beta x is equal to, in fact, it's beta L in this particular case, right? Because we're substituting, we're putting the L in here. So in fact, I'm wrong. This should be beta L. So beta L is equal to n pi. And therefore, we know that beta now is the constant that's set by these boundary conditions, and that constant is equal to n pi over L. So our final solution here final solution for these boundary conditions is equal to the following. So x of x is equal to, come back up, it's C4 sine n pi x over L. And this ends up being our final solution for our standing wave. You'll notice we've got an integer in here. And we also found some integers at the end of an earlier lecture when we were thinking about the patterns, in fact, that come out of waves that allow us to have an integer that kind of ties in with this Rydberg equation. So anyway, wrapping up this particular lecture, we've talked about some differential equations for classical waves. We've thought about oscillatory solutions. Oscillatory solutions make sense. Oscillatory solutions, cosines and sines, these are waves. We can also use Euler's theory to describe cosines and sines, but using exponential terms. So we're going to find that Euler's formula here ends up being quite useful to us. So keep that in mind. I'm going to finish at this point and say everything I've described in this very short lecture is taken from chapter 2 of your textbook. It's very well said in the textbook. It's worth a read. I hope I've got the point across. You're going to see some of these things pop up again and again as we look at our next simplest system that we're going to apply quantum mechanics to, and that's for the particle in the one-dimensional box, which is like the particle, it's like that electron in the butadiene molecule that I brought up in lecture 4. So there'll be lots of questions, I'm sure, but thanks for listening. Look at my notes, look at the textbook chapter, and read those through, and it'll make sense, and it'll be a good foundation as you go forward in this class. Thanks for listening.